My name is Alan Campbell. I'm an SRE lead at Bloomberg. I joined the company back in 2013 as a graduate software engineer. And that was 1 year post-acquisition of a startup called Polar Lake. And I think that's important for the context of today's talk because I've experienced that product, that EDM offering, grow from a startup into a global Bloomberg product offering. So as you can imagine, there's been plenty of challenges along the way. So what is Bloomberg, you might ask? I'm not sure if the audience is familiar with the company, so I'll just do a quick summary. We provide financial data, information and analytics, news and trading platforms for the financial industry. Our data is used to make the most important decisions, or financial decisions, so it's imperative that we provide the richest, cleanest, and most accurate data available at all times. Our terminal product, which you can see here on the left, has over 350,000 subscribers globally and is available in multiple languages. It has a vast amount of data on it, over 400 billion pieces of real-time market data every day. We publish or ingest over 2 million news pieces daily as well. I'd encourage you all to go downstairs. We have a booth down there, and Joe has a 4-screen terminal, even better than my example. And it kind of gives you an insight into the vast nature of the data that the terminal provides. In terms of people then, we employ over 9,000 engineers alone. 350 of those are working on AI and machine learning alone. So whether you know Bloomberg or you don't, I'm sure you've all seen it in many movies that reference financial experts, and they have a prop, and that screen is generally something similar to that. So you may have seen it, or you will see it in the future if you see some of these films or any financial films. So I mentioned Polar Lake, a startup that Bloomberg purchased back in 2012. That's since evolved to DL+. And I just want to give you a quick overview of what that does, because again, it's relevant to the context of today's talk. Essentially, like most data pipelines, we have an inbound, we do some stuff with it, and we deliver to our customers. So we take in various different data sources, many different formats, naming schemes, delivery options, and then link all that financial data together. So it's one consumable file for our customers, and they can consume it in many ways, whether it be SFTP, API, Snowflake in the cloud, whatever it may be. So it saves our customers having to deal with different file types, different naming schemes, different formats. We do the work so our clients can just concentrate on the data. So I just given a hat tip to one of my favorite podcasts, Cautionary Tales with Tim Hartford. And what he does is he talks about some event in the past that caused widespread damage, or there were a lot of lessons learned from it. So I'm going to attempt to do the same today with some real-world failures that happened in the financial industry and some of the lessons or tools we can take from that. Quick disclaimer before I do so. The charts and visualizations I show today are all sample data or AI generated, and the failure mentioned are not Bloomberg issues. So the first failure then just happened this year actually. A European data index provider, several prices were calculated using stale or missing exchange rate data due to a delayed feed. So they continued processing despite not receiving the required data they needed to provide value to their customer. Downstream of that, key financial decisions were made based on that bad data. There was a loss of trust and credibility for that operation going forward. I promise most of the financial talk is over now and we can focus more on what we're here for. So today I'm going to aim to highlight how simple basic SRE practices can help mitigate or prevent disasters along the data delivery pipeline and do it at scale. So I'm going to talk about data ingestion, data processing, and data delivery. And while researching, I found a a good visualization from Data Kitchen. So they talk about the data journey. So no matter what context we all work in, most of us ingest, do some processing, and output data. So the same concepts apply to all industries. And you can see here in the red on the left-hand side, we have Kafka, a database, an FTP server, and we all have our Prometheus checks and exporters and got our free alerts off the back of that, and maybe even we added some of our own relevant to us. But the question I'm trying to ask here is, are we inspecting the data all throughout the pipeline instead of just waiting until the end and saying, was it right or wrong? So these blue ticks are kind of encouraging you to inspect right on arrival, do some checks after you load it into your system, do more each step along the way, because as you know, the earlier you find your issue, the less of the impact and the less a disaster, and it's easier to fix. So again, the guys at Data Kitchen talk about data flowing through a system and being in different states. So we have data in motion, data at rest, and data in use. So each different state is an opportunity for us to inspect the presence of the data or the quality of the data. Is it expected? So when it's in motion, for example, we can inspect the processing rate, the I/O, the download rate, whatever it may be. When it's at rest, we can do a bit more. Are our expectations met? Is this file here in the right time? Is it complete? Is it fresh? Or does it pass our validation checks? And then when it's in use, what's the latency? How quick are our customers getting that data? So different data states require different inspections. So the first thing I want to emphasize is the importance of journey visibility. So like in the early days of Uber, when you ordered a ride, you just see a spinning wheel saying searching for drivers or requested. Customers had no idea whether their driver was 30 minutes away or 30 seconds away. This often led to a high rate of cancellations, even though wait times weren't terrible, or perhaps they were even better than they are today because Uber was smaller back then. But the uncertainty made them feel longer. So what was Uber's solution? It wasn't to get drivers to come quicker or build roads or faster cars. Uber instead added a real-time ETA and a driver location visualization to the map. So as you can see here, and you're all familiar with, I'm sure, you can see the car is en route. Estimated time of arrival is 8 minutes. That 8 minutes is not always accurate. Sometimes the car gets stuck in traffic or whatever, but you can still see it moving along the road. I don't know about you, but if I see the car stuck and stopped for a long time, cancel. But if I can see it moving gradually towards me, I'm prepared to deal with delays. So even if it still took 6 or 8 minutes for the car to arrive, customers feel in control because they understand the situation. They're less anxious and less likely to cancel. They waited more patiently because visibility replaces that frustration. And it's essentially backed by behavioral psychology. People are far more tolerant of the delays when they know what's happening and how long it's expected to take. So similarly, we've applied the same principle to our financial data systems. We show the flow of data through our delivery pipelines, where it is, what stage it's in, and whether it's delayed or not. This here is an example of 7 or 8 runs for a given customer. You can see the green ones are completed. Each step is a green lozenge, and happy days, they're delivered to the customer. You can see 2 are still in flight. One is in the analyze stage, and the other one is in acquire and manufacturing. So again, it's like a progress tracker, and customers can see it moving through the system, and it gives them comfort, and it allows them patience to wait for that delivery, even if it is slightly longer than expected or longer than yesterday. If we drill into that, if we click on one of those blue lines, for example, so if I click on that first one, IOI aim trade, we get a blown-off view of a detailed breakdown of the process and where it's at in that process. So clients don't see this, but on the right you can see job identifiers. So this is for our engineers. If it's stuck in a certain line or there's an error, we've instant access to the logs and the metrics and traces related to that step. Using it allows our engineers to triage more quickly. And again, it gives insight for the clients to see where it is at in the flow, in the data journey. So just like Uber's ETA, it doesn't make the data arrive faster, but it makes the experience better, more trustworthy. Our customers can see that data is being validated, processed, and transmitted. If they know a delay is local or upstream, they know not to blame us. Well, if it's upstream, they know not to blame us. They understand why something is late rather than assuming it's broken. So this builds confidence for our customers, and again, for the engineers, we can triage quicker because we can see where in the step it's broken. So, as I said, Uber didn't fix waiting times, they fixed how people felt about waiting. Now I want to talk about checkpoints along our data journey. So I want to introduce the concept of milestones, a safety measure ensuring we have our certain dependencies are met before we continue processing. Again, back to that failure example I had. If they had some checks and balances on stale data or arrival time of a feed, perhaps they would have had prevented their failure or certainly mitigated it. So one of the steps along of our data journey is checking for the presence of files that are required for a given run. This milestone pauses processing until a file is met. So you can see here we have wait for vendor file loading. So what that is doing, we've configured that for this run, for this customer, we expect or we need this file to be here. Don't continue unless that file is in. Now we do have a manual override. You can force it if the data operator knows that, right, this file is needed or it's not going to come. So we have actions that can be taken in cases of disaster. But in general, we wait until the file comes in. When things do go wrong, again, transparency can be helpful to both the customer experience and the engineer troubleshooting. So a customer might say, oh, why is it stuck here? I'm waiting for a while, it's been here for half an hour. We have alarms to kind of help with that. It's saying expected file upstream of us has not arrived. So there's not much we can do, perhaps contact the vendor, but again, it sets the expectation for the clients that things might be a bit slower because we're waiting on a file. So how does this process work technically? This is our milestone messaging system and just some of the architecture behind it. As you can imagine, our system handles millions of events. And those events are passed through our system via RabbitMQ, Kafka, or basic HTTP calls. So let's take this file example. When the file is in, we send a message saying file arrived. Then we have to download it, we have to place it in our storage. Another event goes file downloaded, file ingested. Then it flows through Kafka messaging queue and sends it to the relevant place. This is an example of one milestone. As I said, file has arrived. It checks the file name and then issues a callback via WebSocket to say, yes, we're happy, this file is here, you can now proceed with your processing. So going back again to our data journey, this is the first point where data is at rest in our system. It's come from a vendor, we've stored it locally. Now we should do some validation on it. It gives us an opportunity to do some quality checks, null value checks, bad characters, the correct format, whatever. Moreover, we can apply some machine learning over it as well. So is it the expected file size? Typically, files day on day are the same size, same structure. Clients have access to the same universe of instruments. But sometimes there could be a market event or there could be a software bug that means that file is bigger or smaller. If it's smaller, perhaps there is a bug in our system. We need to go and investigate. The earlier we know about this, the better. If it's too big, again, it sets the client expectations. Perhaps there was a market event that caused a huge order backlog, and again, their data journey is going to be a bit slower. Once the file has arrived, we're happy, we've completed our validation. The users will see next that their flights plan step is checked off. Processing continue, and the data is in the system, and it meets our quality standards, and away we go. So again, back to that failure, a simple check like this could have mitigated or prevented that disaster. Second disaster, more bad news. Back in 2012, a high-frequency trading firm attempted to do an upgrade of software. One node remained on legacy code and was executing legacy code. This had a high failure rate. So within 30 to 45 minutes, there was $440 million of losses. And the stock dropped 70%. So I'm sure everyone in this room could identify many different ways of how we could prevent this failure. There was talks on config drift yesterday, instance version variation, post-validation checks, simple regression testing once you deploy your new software or attempt to deploy your new software would have shown issues. CI/CD safeguards, automated rollbacks triggered by error rate thresholds. But sometimes problems do occur. We miss it, erroneous software is deployed and running. So again, referencing back to our data journey, we now have data in motion. We want to validate the success rate as it flows through our system. A common tool that, again, there has been great talks yesterday by one of my colleagues and another one the day before around SLOs. We can easily see our SLO is being breached. It's alerting there's a problem. It's too late to roll back the software, or our automated systems didn't do so, so we have to take manual action. But our expert engineer is on vacation, so what do we do? It's important to have emergency runbooks, easily accessible and, more importantly, actionable by a broad audience. Emergency break glass, an off switch. There should be no human-specific dependency. Clear and simple runbooks with no expected prior knowledge can expedite solutions and minimize losses. So when that SLO alerts, it should have a link to your runbook, and it could have shaved minutes off this 45-minute failure, saving millions of dollars. In the financial world, I like to think that instead of better late than never, it's better late than wrong. So pause processing if you know there's a problem, get it right, and then deliver. Once we do deliver, then at the end of our data journey, we deliver our data to the customer. We need to give them confidence that the data that they have received can be trusted and they can validate it. This is especially important in the financial industry as they're subject to compliance and regulation such as DORA or MiFID II. Here, I'm showing Apple stock. So it just has a simple company name just for demonstration purposes, Apple Inc. Where did we get this from? How do we know it's correct? So our software gives data validation and data lineage into it. So if you click into it, you can see 4 files that were queried to see the value for the name of that company. You can see 2 of the files resulted in Apple Inc., and we've selected the first one. So you can drill down even further and see the rule definition that led to that outcome. So first populated value of long comp name in any of these files will result. Now, obviously, there are more complex examples around pricing or linking, but just for demonstration purposes, I'm showing this example. So data lineage is very important to build confidence and trust. We see other examples of this in the wild that helps build consumer confidence. LLM chatbots shows when you send your request, thinking, looking up source X, Y, and Z, and it shows you the path that it's taking to get you a result. And if you do actually watch that, it does give you a greater confidence, and the answer you get is what you're looking for and can be trusted. So as I said, it's essential for our customers when it comes to regulatory and compliance audit, but it builds confidence and customers can trust what we deliver. So now I talked about one data journey for one client or one file. How do we scale that across multiple customers? As I said, I joined back in 2013 and it was a small startup, and now it's scaled to many customers. So here's the flight plan again, one run for one customer on one day. And this is one step in one run for one customer on one day. So we track the outcome of that. We store, start universe export, completed successfully, 100%, and the duration it took. We store all these metrics in a database and we can track them over time. We can see that over the last 6 months, this entire run took on average 33 minutes. A few fluctuations, but generally consistent. We can see each step, what's the longest one. So wait for dependent scheduled runs takes 30 minutes. It's the slowest bottleneck of our run. This is very useful when a customer complains and saying, oh, my run is slow. We can instantly see how each step of that run has went over the past 6 months or longer. And it's very good for triaging in retrospect. Similarly, wait time dependency, and if a file is late, we can tell which customers are going to be affected because the dependency is here. But again, we have many steps, many runs, many customers every day. So finding the slowness can be a needle in a haystack. And we don't want a customer complaining, saying it's slow. We want to find it first, get ahead of it, and reduce customer slowness or annoyance. So again, going back to this specific example, start universe export. It took 1 second here, but we're tracking this over a long period of time, much longer than your typical Prometheus retention period. And we're storing it in a database. And we can see that over the past 6 months, it's taken from 50 milliseconds up to 200 milliseconds. But it's noisy. And we can't have basic thresholds saying, oh, if above 100 milliseconds alert, because you get alerts every week and it doesn't mean anything. The data could have been bigger that day. It's not necessarily anything. So this is where anomaly detection and machine learning algorithms come into play. For example, medium absolute deviation. This can be useful in some use cases, and we have to apply them differently depending on the use case. If we go back to that example, it's not that useful here because we do have spikes that would alert in this case. So instead, cumulative sum is much more useful here. Like the blue image here is similar to the last Grafana graph I showed. It's very noisy, probably trending up, but it's difficult to tell with the human eye. So the Q-sum algorithm checks how it's kind of like counting cards in poker. Is it going up gradually over time, and is that adding up? If it is, then you get a clear graph on the right that's much more readable, alertable, and actionable. Similarly, then we apply other machine learning algorithms to this data on those runs. The financial market is closed at the weekends. It closes at 4 o'clock every day, Eastern time. It's off on holidays. So your expected traffic is correlated to the market and how it flows. So therefore, your alerting has to correlate to that expectation. We can't just have flatline alerts because it deviates depending on the time of year, the time of month, or even the time of day. Once the market closes on a given day at 4 o'clock, we have our end of day runs. So there's a huge spike in traffic. So Facebook's Prophet machine learning algorithm helps us handle that load, predict that load, and alert based on it. K-means is another one that we find useful because it groups our customers into specific usage patterns. Some customers are sporadic and erratic, and we can't predict at how they will use our system, but we know that we can predict it, and that in itself is useful. Other customers are heavy users. They run the same type of runs every single day at the same time with the same load. And again, in times of trouble, it's important to know that. so that you can act appropriately. The next topic that I want to talk about is having a safety valve. As I mentioned, we saw a huge increase in customers in a short space of time. And we don't necessarily have time for building full-scale load tests and chaos and engineering in our dev and beta environments. So instead, we introduced that 20% of our load in production was internal demo test clients. So then, as we're scaling up, we have more customers all the time. Different bottlenecks appear like whack-a-mole. So when we feel the pinch, we can automatically just turn off these internal demo tenants fully, or even one by one, to reduce it by 5%, 10%, or up to 20%. We instantly have a 20% headroom, and we have telemetry on our next bottleneck. So this gives engineers, the next morning, we don't have to call them because we've given them 20% headroom of our system. The next morning, our engineers can come in and say, oh, our demo tenants had to be turned off last night. Why? So all our metrics, logs, and traces will have recorded that slowness, and we know our next bottleneck. We can address it with time and without panic or in an incident. So it's rudimentary, but it's effective and it buys time. Obviously, as we get more mature, we do more of this in via load testing and chaos engineering in our dev and beta environments. But I don't know, I like this in production, so I intend to keep it for a while. Another tool which has proven useful during this scaling period has been working with our sales team. So connecting to their sales pipeline and getting early insight into potential customers that are coming down the line. We compare potential customers' configuration and feature set to past and existing customers' feature set and configuration. What is their compute costs, storage costs, how many jobs and HTTP calls do they typically make? This gives us time to ensure that we have capacity to onboard, and we can work with sales and say how much we can onboard in a given time frame. Many customers have a different profile, so we can speak with our infrastructure team and tell them how many customers we can fit of different profiles into our existing compute, and decisions then can be made. Do we need to increase our compute or maybe even refactor the code to handle this upcoming customers? It's not an exact science, but it gives us an insight into expected load. So then I also want to talk about rate limiting. So another tool that really solved a problem was just basic rate limiting. So customers are hungry. If we give them a successful product that's delivering data, they like it, they're going to use more of it. So in this example, I have customer A, B, and C. Customer A is trying to submit 5 jobs, and jobs are just work items along that data journey that I spoke about before. So customer A has 4 work items at the top of the queue. So as you can imagine, without any limits, first job goes on the executor, second job, third job, and fourth job goes on at my executor. And now it's saturated. So customer A is happy, but customer B and C are not happy. They can't see their data flowing. They can't see their Uber car driving or making progress on their way to them. So simple but effective way of handling that is just putting limits per customer. Having a default. So you can see here, default is 1. Customer B doesn't have any specific configuration, but he inherits the default of 1 executor concurrently. Customer A has a special config of 2, and customer C has a special config of 2. So now instead, yes, customer A is a heavy user. It has 2 concurrent jobs. Customer C has 1, and now customer B has 1. So instead, all our customers can see data flowing, data moving, and progress along their path. So in closing, I just want to leave you with some thoughts. Buyer beware. Just like our infrastructure or application alerts, the same concepts apply. More alerting is not necessarily better alerting. Beware of alert fatigue. If alerts are not real issues, then soon all alerts will be ignored. So less is more. Value signal over noise. Finally, then, the key lessons that I would like you to take away today. Give your customer insight and information about how things are going. Communicate problems early and often. They tend to be more patient and understanding with delays and processing problems when they are aware of them. Even with the smallest alerts, tests, or guardrails, we can prevent outages. We don't have to build large generative AI to fix our problems. Sometimes a simple post-deploy validation check or a drift detector can avoid potential disaster. Having an easy off switch. As I said, instead of better late than never, I think in finance, better late than wrong applies. And I'm sure to many of your industries too. So keep adding small checks and guardrails. As I said, it doesn't have to be some revolutionary process. The small but effective often works. We won't ever be airtight. There's always unknown unknowns or upstream problems or outages beyond your control. So just like fire safety drills, having plans for failure is vital for navigating failure and minimizing impact when failures do occur. So thank you. And before we go to questions, I just want to highlight that, as I said, we're here in Dublin, we're hiring, and we have a brand new office. Mike Bloomberg actually just came over in the past few months to open it. And as I said, there are open positions. Go downstairs, talk to Joe, and yeah, thank you very much for your time.